Welcome and thank you for joining. Let's take a look at one of the homework questions from Qualitative Graphing. This is when we're given features of the graph of a function and we have to sketch the graph and possibly create an equation. So we're looking at question number 6, which asks to write a polynomial function with degree greater than 1 that passes through the points 0, 1, 1, 1, and 2, 1. So we're going to take a closer look at the information given here, which is only these 3 points. And we're going to try to find a meaning in each and every one of them, see if they mean anything significant to the graph, such as an x-intercept or a y-intercept, etc. So whenever you see that one of the coordinates is 0, you have to look for either x or y-intercepts. So in this case, x equals 0 and y equals 1. And remember that x equals 0 at any point on the y-axis, which makes 0, 1 the y-intercept of this function. Now, the next 2 points have their coordinates 1, 1 and 2, 1 respectively, and these 2 points don't seem to be either x or y intercept, so these are just ordinary points on the graph. So the next thing that you want to do is try to plot the points so that you can see if there is any relationship between them. Now, for some of us, it's easier to kind of see a relationship between the points. And by relationship, we mean if they have anything in common. You probably notice that the y-coordinates at all 3 points are the same. But if you don't see this right away, try to put this on the coordinate grid so that you can visually understand what relationship may exist between them. So first of all, I will plot the points, scale, eyeball it. So first point is at x equals 0, y equals 1. The second one is at x equals 1, y equals 1. And the next point is at x equals 2, y equals 1. I will mark the 3 points to make things perfect. I will label the axis, the y and the x-axis. And as you notice, the 3 points lie across a horizontal line. So they're aligned on the line y equals 1 because their y coordinates are equal. So we need to draw the graph of a function that satisfies the condition that the graph will pass through the 3 points. Now, to bring this idea a little bit closer to us, I'm going to draw a polynomial function, right? And as you can see in here in this polynomial function, you can draw, let's say, for example, the x-axis and or any horizontal line. And if you draw any horizontal line, you will see that points will have the same y coordinate at each and every one of them. So polynomial graphs, as you know, are curves that go up and down, okay, and depending on what type of factors or coefficients we have. So one may go higher than the other or lower. And as you can see here, for example, you have 1, 2, 3, 4 points. So if you were to move this line, right, elsewhere, so you can have, let's say, 1, 2, 3 points here. You have 4 points in here. You have 3 points of intersection here with the same y coordinate, 1 point of intersection. So you get the idea. The reason why I'm showing this or demonstrating this exercise is to see the variety of possibilities that we have given this little information about the graph. So one of the graphs that I can draw in this case would be a graph that is going down and then up again and then down again. So this can be a third-degree polynomial function with a leading coefficient, as you can see here, that has to be a leading coefficient of 0. Or we can also build a graph that starts low and then goes higher and then goes up again. Or we can draw graphs of higher degree higher than 3. And for example, in this case, I would bring the example of a function that will go lower here, higher, make a turn, and then come back again. Oops, sorry. So we can also have the graph of some function that goes high, low, make other turns, and goes back again. So the degree can be higher than 3 obviously. But the idea is to create only a polynomial function, which means that either one of these examples would work. So again, the only reason I brought up the idea of making more curves above these axes is just so that we can show that there is probably an infinite number of equations that we can create, or infinite number of graphs that we can create that satisfy this condition. So we're going to stick for now with a third degree polynomial function. So I'm going to draw the graph, or I'm going to try to write the equation of the pink graph. Now, if I were to draw the equation of the pink graph, which I'm going to call f of x, then the x-intercepts have to be 1 to the left of x equals 0, and the other two x-intercepts have to be between 1 and 2, because that's where the graph has to pass. So the x-intercepts can be, let's say, at 1/1/3 and 1/2/3, for example, at this point. So I'm going to call these 2 points the x-intercepts of x equals 1 and 1/3, which will make it, let's say, for example, 4/3. And the other x-intercept here would be at 1 and, what did we say here? I'm going to make it 5/6, for example. It's very close to 2. That will make x equal to 6 times 1 plus 5, 11/6. So we're going to say that we already have these two x-intercepts. And again, these are values that we can create. So this is an open-ended question, so it's not a question that has a definite answer. And this x-intercept would be, let's say, for example, at x equals -1/2. So we have the equation of some polynomial function with indicated zeros. We have chosen the coefficient a here to be positive. As you can see, the graph stretches from quadrant 3 to quadrant 1. And based on the x-intercepts, I will create the equation. So if x equals -1/2 is one of the roots I decided to consider, it means that 2x equals -1, or 2x plus 1 equals 0 is one of the factors we have probably used to find the x-intercept. X equals 4/3 means that 3x equals 4. Again, this is the reverse process of solving an equation, so we are unsolving it so we can discover the factors from where the x-intercepts have come from. And lastly, we have x equals 11/6, and that means 6x equals 11, from where we're going to say that 6x minus 11 must have been one of the factors. So here we go again. We have 2x plus 1, 3x minus 4, 6x minus 11. And we're going to bring them together, 2x plus 1, and then 3x minus 4 into a big product to create the equation of this function. Now, you're probably wondering, okay, so this is one equation that we can draw, and we didn't definitely determine the value of a. And my next question that I'm asking myself here is it possible to find the coefficient a given this much information? And not only given this much information, but also the extra information that we have input in this problem. So as you can see, in this case, we are given not just 1, but 3 points on the graph. So we can use either point to determine the coefficient a, and we're going to do this by using my favorite point to use in finding the y-intercept. I mean, to find the coefficient a, which is the y-intercept. So y-intercept, which is at x equals 0, y equals 1, is the best point to use, or I should say the better point to use to find coefficient a, to determine a. So here we go. We're going to say that 1, which is the y value right here, would be equal to a. So this will turn into a 0, this will turn into a 0, and this will turn into a 0. So 1 equals a, 0 plus 1, and then 0 minus 4, and then 0 minus 11. So 1 equals 1 times -4 times -11, 44a. So if I wanted to give this an a value, that would be equal to 1 over 44. So the equation of this function, this particular function we chose in here, would be f of x equals 1 over 44, and then 2x plus 1, 3x minus 4, and lastly 6x minus 11. And voila, this is a possible equation that passes through these 3 points. Obviously not the only one, but if you want to check and see if this is a correct equation that satisfies these conditions, and you can draw the graph on Desmos and check and see at y equals 1 what the x values would be, and check and see if this will be true for the graph. And that's how you would check your answer and your thinking using Desmos. All right, I hope this made sense. Thank you for learning with me. Bye for now.